you for coming. Well, Robert Bob Oliver is an emeritus professor in the University of Paris, Spain. He obtained his PhD in Princeton in the 70s. He has been a professor for many years in Aarhus in Denmark. He also had a position in Stanford. And he has made, well, major contributions in topology and in algebra, in particular describing fixed points of actions of finite groups in acyclic complexes and in this. Also, he has important results in the computation of lower K groups in K theory, and he's one of the fathers of the theory of fusion systems, which connects some local algebraic properties of finite groups with topology. I think he will say some of this in this talk. And well, it is always hard to convey what is the value of results in one area to people in other areas. Here we have different areas. So let me just say that if we count among his publications only those which appeared in Annals, Invenciones, Acta, and Jams, he has 11 publications. So this is a detail. So well, it's a pleasure then to introduce Bob Oliver. He will speak about local structure of finite groups and of their classifying spaces.
Okay, well, thank you, and especially thanks to Jonathan for inviting me here, giving me the chance to visit Buenos Aires for the first time. So, okay. Title, Local Structures of Finite Groups and of their Classifying Spaces. So, first thing I want to do is talk about what I mean by that title, what I mean by local structures of finite groups, local structures of spaces, and then state a theorem. So, first, on the side of the finite groups, well, first I'll start off with a very loose, imprecise definition. So let's say P a prime. So the P local structure of a finite group G is roughly, it means a Celoff subgroup of G, or the structure of a Celoff subgroup, together with conjugacy relations among subgroups and elements of S, of the fixed Celoff subgroup. So, as I said, that's not very precise. And to make this more precise, and what's easier to state exactly is what I mean by two finite groups having the same P local structure. So, G and H, finite groups. Then I'll say that G is, I'll write it this way, G is P locally equivalent to H if you can find CLF subgroup S, a CLF subgroup of G, T, CLF subgroup of H, and an isomorphism between them. Yeah, okay, I already called it phi. With the following property. So the CLF subgroups have to be isomorphic, but it's stronger in that for every abstract isomorphism between subgroups of S, alpha is given by conjugation in G, is conjugation by some element of G, if and only if the corresponding isomorphism is given by conjugation by some element of H. So this would be from phi of P to phi of Q. So what these symbols mean is that they're conjugation some element of G or H respectively. Okay. So just as an example, the simplest example probably, one can A6, so the two alternating groups, A6 and A7, are two locally equivalent, but they're also two locally equivalent to, say, PSL2 7, PSL2 25. One can keep going. There's a whole bunch of them. But not two locally equivalent to symmetric group S4. And note that all of these have CLF subgroup a dihedral group of order 8. So that part is, I mean, one has to check it, of course, but it's not hard to check in each case that they all have dihedral CLF subgroups. But note that in the first 4 cases, all elements of order 2 in a given CLF subgroup, well, or in the group, are conjugate. But, as is well known, not in S4, since you've got transpositions and products of 2 transpositions that are not conjugate to each other. So, of course, this observation is not enough to prove that this holds, but in fact, it is true that one can show that any finite group with CLOF2 subgroups isomorphic to, well, dihedral of order 8, and which have this property, all elements of order 2 are conjugate to each other. All of them are 2 locally equivalent to A6 and all of those others. Okay, so that's the first half of the picture. Now to look at spaces. Again, fix a prime P. And I'll say that 2 spaces are P locally equivalent. If there exists a diagram, the following form. Well, if there exists a third space and maps from X and Y to that third space, such that in homology with coefficients mod P, they're both isomorphisms. Okay, so in other words, not requiring that these be homeomorphisms or homotopy equivalences, but just basically that at, as far as you can tell from algebraic invariance localized at P, they're equivalent, they're the same. So, for example, projective plane is P locally equivalent to a point for all odd primes P, but of course not for P equal 2. Okay. Just want to make one comment about this, namely, note that this is a the relation is transitive. Which can be shown fairly directly. If we've got say W, P locally equivalent to X, P locally equivalent to Y, well, means you have some situation of this form. And now you can take a kind of push out here, where you take the union of these 2 spaces and this space crossed with the unit interval. And I'll write it this way, identifying here using G0 and here using F, because more precisely, we're identifying, say, for all x and x, x0 is identified with G0 of x. And x comma 1 is identified with f of x. So it's what topologists call the homotopy push-out. It's slightly more flexible notion than the simplest form of push-out. But the important thing is that these maps, standard tools in algebraic topology show that these maps are also induce isomorphisms in mod P homology. So all maps in the diagram are homology equivalences, and therefore you have W equivalent to Y, because you just take those composites. Okay. So those are the two halves of what I wanted to talk about, finite groups and the spaces. And now, to link the two together, that's where the classifying spaces come in. Okay, so I'll define this for any discrete group. Including the case of infinite groups, just because the simplest example to give is the case of the integers. So I don't want to exclude that. So infinite or finite, and now classifying space for G. So space, or usually some sort of cell complex or simplicial, usually when one puts on some other conditions. Simplicial complex, which I'll call BG. Well, I'll give two ways of formulating it. First, in terms of covering spaces, the requirement is that the fundamental group is G, and the universal cover is contractible. So, in other words, continuously deformable to a point. Then the second let me give a second definition that avoids talking about covering spaces. Or you could say sort of defines the covering spaces in the instruction. So an equivalent definition is that there exists contractible space E with proper free action, define that in just a minute, of G, whose orbit space is BG. So, by a proper free action, meaning that for every point in E, there's a neighborhood, open neighborhood, such that the subspaces are pairwise disjoint. Okay. So, okay. The simplest case, and as I said, the reason I wanted to include infinite groups here, it's the case of the integers. So, example. So, when G is the integers, take E to be the real line. Integers act by translation. And you can take C to be just quotient R mod Z, which is easily identified to the circle. Okay. So the circle, in other words, is a classifying space for the integers. Want to do it for finite groups, things become harder, mostly because it turns out that the classifying space of any finite group, finite non-trivial group, is infinite dimensional. But so, simplest case, let's take the case of G group of order 2, and I'll think of it as just group plus minus 1. And now I'm going to take E to be the infinite dimensional sphere, by which meaning the union of the finite dimensional spheres. Under the obvious inclusions. So in other words, it's the unit sphere and the infinite dimensional space of all finite sequences of real numbers. And G acts on E by sending x to minus x, or the non-identity element exchanges x and minus x. So B of group of order 2 can be taken to be, so E mod G, and that's the infinite dimensional projective space. Okay, well, one thing I skipped over quickly we're using here that S infinity is contractible. The usual way of showing that is using algebraic invariance to, homology and homotopy groups and so forth, just by taking this union and taking some form of limit. But one of my colleagues, who's actually an analyst in PDEs, pointed out the following much simpler argument. Because we can, so if we start off with S1, then we can identify that with the boundary of the 2 simplex. So just the boundary of a triangle. So embed that in S2, which can be identified with the boundary of a 3 simplex. So now okay, sort of the idea. And I won't try to draw them any further. But of course, it's obvious what one does now. And if you look at it this way, then when you take the union of all of these boundaries of the simplices, that's convex and hence automatically contractible. Or simpler way of saying that, maybe, is that this thing, the union of the boundaries is equal to the union of the simplices themselves. Because whenever you start off with a boundary of a simplex, but at the next stage you fill it in. You add on the simplex itself. Okay. So now, state the theorem that links these two together. Started off as a conjecture by Martino and Pretty. Says that for all G and H finite groups, for all primes P, BG, P locally equivalent to BH, if and only if G is P locally equivalent to H. And now, of course, I'm not going to prove it, but just going to note that in one direction, this implication was proven by Martino and Pretty. And uses well, various things going back to the Sullivan conjecture. So it's what I think of as the easy direction, although it's all relative. Was easy only before Sullivan conjecture was proven in the 80s. It was far out of reach. And then the converse has a more complicated history that I gave a first proof. And then, well, let me just write down the names. Then Chermak gave a second proof, and Glauberman and Lind. Well, I write it this way. The first two proofs use the classification of finite simple groups. Which is why, from the beginning, they were considered quite unsatisfactory. My proof just involved a very laborious case-by-case analysis of basically having to go through the list of simple group, well, reduced to a case of a question about simple groups at each prime, and then just having to go through the list. Andy Chermak, around 2011, came up with a much simpler proof but which still relied on the classification of finite simple groups. But it was his proof that made possible the proof by Glauberman and Lin. They showed how to modify Cheremak's proof to eliminate the use of the classification theorem. So final result is a proof that's independent of the classification of finite simple groups. Okay. Let me make one more remark about this implication, that it's a refinement of a theorem, maybe what's called the stable elements theorem. Of Cartan and Eilenberg. Who showed that, said that for S, a Celoff subgroup of G, the homology of G with, well, let's say, mod P coefficients can be or is determined by homology of S and P local structure in a way which, of course, they made precise. But the important thing is that, in particular, if G and H are P locally equivalent, that implies that they're homologies. And here I'm just talking about group homology, that they're isomorphic. Okay. But one of the properties that I didn't mention of classifying spaces is that the homology of the classifying space is isomorphic to the homology of the group. In fact, I think that was part of the original motivation for defining group homology. And so the Cartan-Eilenberg theorem really states that if G and H are P locally equivalent, then they're classifying spaces, then the mod P homology of the classifying spaces are isomorphic. Well, so that's a weaker statement than saying that the classifying spaces are P locally equivalent, because P locally equivalent, so saying that it implies this is a refinement in that it says not only are these two groups isomorphic in some abstract sense, but the isomorphism can be realized by maps between spaces. Okay. Okay, so now for one application of this, so this is a theorem that I proved with Carlos Broto and Jesper Müller. So make sure I get all of the. Okay. So now let G connected. I'll explain what this means in just a minute. Reductive group scheme. Over the integers. Yeah. And now P's prime. Q and Q prime are prime powers, both of which are prime to P. Okay. So then if Q and Q prime, so I'm taking inside of p-adic units. So Q and Q prime, they're prime to P, so they can be regarded as units in the p-adic integers. And one takes the subgroup generated by them and take its closure in the p-adic topology. And so if those two are equal, then that implies that G, the prime over the field of order Q, is P locally equivalent to G over field of order Q prime. So let me just give some examples. So connected reductive group scheme, I think of a group scheme as a functor from rings to groups with certain properties. And in any case, you can take SLN, GLN, PSLN, symplectic 2N, I mean, the usual candidates, G2, E6, Okay. So the standard Lie groups that can be defined at over any field or any ring. So this says, okay, so if Q and Q prime generate the same closed subgroup, then the corresponding groups are p-locally equivalent. And then there are a couple more similar results. Let me just state this one. I'll forget the third one. But minus identity is in the Weil group of G. And then this implies that same conclusion. And then there's a third one that there's not time to mention. And now, to make this a little less mysterious, when p equal 2 and Q prime are odd, then Q and Q prime generate the same closed subgroup of the two adic units, if and only if, well, Q congruent to Q prime mod 8 and the two-adic valuation of Q squared minus 1 equals the two-adic valuation of Q prime squared minus 1. So this meaning the largest power of 2 that divides it. And so now one gets, so 2 applies to the case PSL2, and that's why we get PSL2 of 7, 2 of 9, of, I'd have to think, but 23. And you can keep going. Maybe I can just remark standard fact that PSL2 of 9 or F9 is isomorphic to the alternating group A6. And so that brings us back to the examples I gave at the beginning. So this includes most of the examples in that equivalence class, although except for A7, which doesn't have that form. Okay, so I'll stop there.
immediately will come a mention of this simplicial complex associated by equivalent to the zero subgroups.
Oh,
You mentioned in Ivan's thesis, but this
no.
it has nothing to do with that.
Very well. If you take it far enough, eventually, it's rather distant. No, because so you can think of this p-local equivalence of groups. That's a way of talking about. I mean, it says that it's a way of saying that the fusion systems are equivalent without defining fusion systems. Well, a fusion system is just, well, it's a category whose objects are the subgroups of S, and morphisms are given by conjugation in G. So that's encodes all of this p-local information. And yeah, equivalence complex does come up occasionally when, actually, it's very indirect the way it comes up. Yeah.
I have one. So in your proof, I mean the difficult one, when you prove that the classifying spaces they are equivalent, do you really need this third space of the definition, or is just that you find a concrete map from one to the other?
Well, again, well, okay, in general, there is no concrete map from one to the other. But what we do is we have to talk about p-completion, something else that I avoided very carefully to talk about here. So saying that two spaces, well, let's say under certain conditions, let's say at least, if we're restricting to spaces with finite fundamental group, then they're p-locally equivalent if and only if their p-completions in the sense of Bausfield and Kahn are homotopy equivalent. And so we the idea that, well, the starting point of the proof was work with Broto and Levy, where we constructed a category that's sort of an extension of the fusion system, a slightly larger category, where we showed that, so that's what we call the linking system, and then we showed that BG and BH are p-locally equivalent if and only if the these linking systems are equivalent as categories. And there we really it was really a question of showing that the p-completions are homotopy equivalent. And then afterwards we can, using this algebraic interpretation, we can work out an obstruction theory, which is analogous to the obstruction theory for group extensions. And then so everything else was reduced to that, to studying the obstruction groups or showing that the obstruction groups vanished.
Any other question? Okay, if not, thank Bob again. So thank you.